Hello class, in this video we are going to talk about how to build the Lego furniture problem with Excel and how to solve the problem with the solver. So here, this is the description of our model, at least here um, in the mathematical presentation. And these are the basic data we have, which corresponding to the equation here. And here we would have our here we have the coefficient for the number of for the tables and chairs we produce. So for each unit of tables, then we will have net profit of selling price minus the um, small blocks it requires, which is 2. It requires 2 small blocks, and if you multiply by the price of the small blocks, which is B4 minus the amount of big block it requires, which is 2, multiplied by the cost of the big block. We log the price of small and large blocks so that we can replicate these cells. So that's exactly what we have as the coefficient to this problem, which corresponding to the unit profit they can earn by selling a chair or table. So the table and chairs, which will be our decision variable, let's just set for 1 as 1. The coefficient we have is from here, which corresponding to the unit amount of label or small block or large block used to produce one chair or one table. So on the left hand side correspond to these, which are the total amount of resource you use to produce this number of chairs and table. So we're going to use sum product function. So you have to recall what this function would do. It's basically to take a product first and then do summation. For example, in this case, it's basically 1 multiplied by 3 plus 1 multiplied by here is 2. The unit, the labor hours you consume produce 1 chairs. And then they sum these two products together. So that's what a sum product is doing. So in this case, it's 5. We can drag this down to see different. So to see the usage of different resources. For example, in this case, when double click, it's basically calculate to produce 1 unit table and 1 unit of chairs was the amount of total large block you used, 3. And the right hand side is just the total amount of resource we have, which is called P as here. So these, and we add these signs by ourselves. So in this case, is less than because the total amount of resource we have, we use had to be less than the total amount of resource we have. Then the objective function is just the profit margin we can earn by producing this amount of chairs multiplied by their unit profit. So that's our projective function. So you will notice that some product will be very and super useful in building these linear programming models, because we have these product and summation terms for these variables. Now we are ready to use the solver to solve the problem, since we already have the model built. So the solver will be data, and solver is an Excel add-on. If you don't see it here, you need to add it in a file and option. I believe I've shown that in class, so I'm not going to show it here. So this is the interface for solver. First, you have to set your objective function, and in this case, it's the total profit you earn, and we want to choose maximum because we want to maximize the profit. The changing cells, which are the decision variables. which is here. Then the constraint, and then we need to add a constraint to this problem. We just click add, and note that we can actually add multiple constraints at the same time. So we can drag this all together, and it's less equal to. So we're going to choose less equal to. And on the right hand side is this. So we're going to highlight these three cells together and click OK. So we see this constraint, we just add. Now we can collect this, make unconstrained variable non-active, make variable non-active. We can choose the simplex LP, which is the solution method we're going to choose. And we can click, we can look at the option to see what kind of things we have. You can choose the precision to the problem because sometimes you couldn't find the exact solution, or it takes a lot of iteration to find the exact solution. So it's generally good to have a rough solution. So in that case, you can set the constraint precision, and it seems that's the basic setup. We're just going to use the default setup. So click OK and click solve. And as you see here, we're originally from 1, 1. Now the solution is 2, 2, which is the optimal solution, which we describe on a graph. And we're going to check this, keep the solver solution, and we're going to report the answer, sensitivity, analysis limit, because just for the purpose of seeing this report. So let's press OK. And you see we have 3 reports here, and the solution is already on this. And this is the object function we have. So with that, let's first look at the answer report. It basically says our original value is 1, 1, and the final value is 2, 2. So as you see, we changed our original solution and get to the optimal. And it also says the constraint, where the constraint is binding here. So for the label hours constraint is not binding. If you remember, let me drag this out. Look at the graph. If you remember the graphic solution here, we see not this one. So if you look at this optimal solution slide, we see the optimal solution is here, and the label constraint is beyond this point, which means the label constraint is not binding. We have some label hour left when we make this amount of chair and tables, so it's not binding. But small block and large block is binding, meaning we use up all the label small and large block we have, because this point is on these 2 constraints. What does binding and non-binding mean? Basically, for the non-binding constraint, adding this constraint does not increase your objective function. For example, if you increase labor hours, could you increase your objective function? No, because you will not. This additional labor hours is not valid to you. You already have some left. Additional labor hours does not add values. That's exactly what the sensitivity report would say. For example, in this case, the shadow price, which represents was the value of additional amount of resource. So for the labor hours, the shadow price is 0, because increasing the labor hours does not change your solution. You already have labor left over, so adding more does not matter to you. However, for small blocks, if you increase by 1 unit, you could increase your objective by 3.5, because now with more small blocks, you probably can produce more chairs or tables, so you can increase your profit. Same with the large block. And these shadow price is a very critical concept in linear program. So I couldn't emphasize this less, and it would definitely appear in our exams. So make sure you understand this shadow price. And in the next video, we're going to talk more about the shadow price and also these terms, allowable increase and decrease, as well as these for how does that mean for these variable cells. So that's all for this lecture. Thank you.